Imagine building a medical AI to spot a dangerous mutation. It's an incredibly rare anomaly, appearing in 1 of every million patients. The standard approach is to train a binary classifier, a model that looks at a patient's data and makes a yes or no call based on a single decision threshold. You run the model on your test data, and the initial result is staggering. It scores a 99.999% accuracy rate. But the data hides a mechanical cheat. The algorithm achieved that score by predicting no for every single patient, missing the disease entirely to protect its statistical average. In imbalanced datasets, accuracy is highest when the model is extremely conservative. By shifting the decision boundary closer to the distribution of the rare class, the algorithm minimizes false alarms from the healthy majority, even if it ignores the sick patients completely. Evaluating a single threshold fails to show if the model captured a predictive signal or simply parked its boundary in a mathematically safe zone. Picking a decision threshold before mapping the model's entire predictive landscape is the single greatest trap in machine learning evaluation. To fix this, we have to stop looking at a static cut point and treat the model's decision threshold as a continuous dial of suspicion. Visualize the model's raw output as 2 overlapping bell curves. A threshold far right demands absolute certainty. Sensitivity is 0, but specificity is perfect. Sliding the line left into the overlap catches true positives, but false alarms inevitably creep in. We need a way to mathematically map this sliding scale of trade-offs into a single unified picture. We plot this on a 2D graph. The y-axis tracks sensitivity, while the x-axis tracks false positives. As the threshold turns, a continuous line is drawn across this space, charting every trade-off scenario. This shape is the receiver operating characteristic, or ROC curve. The ROC curve algorithm calculates the coordinates for every possible line of suspicion you could draw, exposing the model's true dynamic range. Now that we have mapped every potential threshold into a single curve, we can finally grade the model objectively. We use a metric called area under the ROC curve, or AUC, calculated via the ROC-AUC score function. To see what it measures, compare these 2 shapes. Plot A is a perfectly diagonal line with an AUC of 0.5. Plot B bows sharply into the top left corner, reaching an AUC of 0.95. That straight diagonal line means the model is guessing. Lowering the threshold yields just as many false alarms as true catches. But the curve in plot B shows strong separation. The model identifies almost all true positives before it starts triggering significant false alarms. This is how researchers prove one model's superiority. In this chart, the GAM model reaches an AUC of 0.98, clearly dominating the tree and weighted tree variance. Because the GAM curve extends closer to the top left, it is mathematically guaranteed to provide a better classification rule, regardless of the real-world costs of a mistake. AUC identifies the model's ability to separate 2 groups. It is a stable measure of performance, independent of where the final decision boundary is placed. We've explored sliding thresholds and probabilities, but some problems require a single, clean boundary that no data point is allowed to cross. In our next episode, we'll look at how margin-based methods like SVMs algorithmically draw this line.